Okay, hey everyone. So today I'm going to be talking about how to create hypervolumes for trying to get an idea about the realized niche of a disease. And this is all going to be done using the hypervolume package in R, which is available on CRAN. It's done by Ben Blonder and colleagues. So just to start out, what is a hypervolume? And in general, hypervolume is a concept, and it's been used to understand what a niche is. And it's first proposed way back in late 50s with G. Evelyn Hutchinson, where he was defining a niche as an n-dimensional hypervolume. And the general concept is that it's these range of conditions, think of all environmental variables that are required, whether it's biotic or abiotic, to permit a species persistence in not necessarily, at least for realized niches, it doesn't have to necessarily be for in perpetuity, but in general, for a fundamental niche, you're looking at for long-term species persistence and suitability. And for a long time, this has taken a lot of different forms, but in 2014, it was adapted by Ben Blonder out of Arizona State, who created the hypervolume package that was available in R. So in general, there are two main methods that Blonder proposes for delineating a hypervolume. And one is using multivariate kernel density estimation, which is essentially understanding the probability density for occurrence points. It's been mentioned that this is preferred in low dimensions, and a lot of the reason for that is because as you increase in dimensions, the density becomes a lot more constrained. And the hypervolumes in general in high dimensions become more and more clustered together. And Blonder originally mentions that this is for really fundamental niche modeling, because the idea is that you're not letting it all possible areas are suitable, and then you're trying to gain probabilistically where the organisms might be present. But of course, in the context of disease systems, that's going to depend a lot on which disease you're working with. Of course, what I'm doing with prion diseases, and because of their strange nature, we don't necessarily believe that areas are completely inhospitable for prions to exist, just based on the experimental records that have been found so far. But by definition, of course, with multivariate kernel density estimation, no areas are completely unsuitable. And this is just because of the inherent nature of the probability density functions that are used to understand the shape of the hypervolume. In general, you have to believe the data that you're using are unbiased. And then they are a good representation of the actual probability distribution. So in disease contexts, you're going to be looking at areas with potentially very good surveillance to be able to understand this. And then the next way to kind of identify, or the next way for delineating a hypervolume, Blonder proposed in 2018, the use of a one-class support vector machine. And of course, this is like KDE, this is another machine learning technique that, unlike multivariate kernel density estimation, which relies on density, of course, and probabilistic density, this one actually classifies whether things are completely in or out, depending on the classification. And so Blonder then later goes on to talk about how this is more of a realized niche modeling application, but again, this is kind of debatable depending on the disease system. And because of the nature of how support vector machines work, this is more recommended if you need to do high dimensional analysis, because the way that it's going to work is more conducive for higher dimensions, because it doesn't matter if it's constrained. Okay, and so one of the ways to delineate hypervolumes, like I said, is with kernel density estimation. And it kind of builds on this idea that species responses to environmental conditions are going to be observing these Gaussian curves, where it would be a normal probability density. But of course, KDE, which is a non-parametric way to estimate the probability density function, one of the ways that it does this is relying on a smoothing parameter to kind of fit this feature, and that smoothing feature is called a bandwidth. In general, smaller bandwidths lead to overfitting, and you have the potential where increasingly large bandwidths lead to underfitting. And in general, the kernel component in KDE is going to be evaluating how far away points are from one another iteratively to then in a probability density, which is then going to provide padding. Down here you have a Gaussian probability density, where of course you have areas around the mean, and then within standard deviation of the mean is the most probable. And then the idea, at least how it applies in hypervolume contexts, is that as you'd be combining two Gaussian curves in 2 dimensions, then you'd be looking at something more of an ellipsoid-based shape, where highest probability is then going to be within the center, and it's going to be radiating out. And then, of course, if you add a 3rd dimension, that's going to be taking the form of an ellipsoid, 3-dimensional ellipsoid. And then, of course, you can potentially add more and more dimensions. And then this figure, like I had kind of highlighted, is a explanation of how different bandwidth selection here can influence the curve. So as you can see here, bandwidth selection is the highest. It's going to be providing this curve right in here, which is going to actually be a pretty smooth, fairly accurate representation of the kind of reference probability density, which of course this is just derived from a random sample of a normal of some normal variable. So then the other method that I mentioned is support vector machine, which is supposed to be a supervised machine learning algorithm that's used for classification. The general idea behind it is that, say you have 2 different kinds of variables and you need to find a classification in 2 dimensions in this scenario. You would be looking for placing a line. But of course, the division between classifications in some contexts can be pretty hard to identify. So one method to be able to get around this is by transforming the data. And then it's kind of this idea called the kernel trick, which then will be transforming the data and then finding some optimal boundary, which is then going to be used to classify. So in the context here, you can use the clustering that's found within this different class, and then actually increase the dimensionality to then create a classification plane like this. And as you could probably imagine, actually transforming the data is really computationally taxing. So instead, you can rely on this method called the kernel trick, which kind of will perform this using a similar method for kernel by evaluating the relationships between points as if they are in higher dimensions, where each relationship is going to be iteratively examined for distance in Euclidean space to then identify what's in and what's out. But of course, by doing the kernel trick, you don't actually have to transform it physically. So in general, with realized niche modeling, there's kind of 6 major steps, and this kind of contrasts to other realized niche modeling, because here we're going to be working on cleaning occurrence records, organizing the environmental data that you need to plug into your hypervolume, and then you need to, of course, extract your data from the occurrences. Of course, model construction is a huge component. You can spend a lot of time on that. And then finally, you're going to be projecting and evaluating your model. So generally with occurrence records, the only thing you need within the hypervolume package in R is just a CSV file with only longitude and latitude in that order. So just 2 columns, however many occurrence records you have. You will actually need to lose the record of species or anything like that, which is a little more common in other niche modeling algorithms and programs. Like always with occurrence records, you should consider spatial thinning, either in geographic or environmental spaces, which will then reduce either redundancy in environmental space or autocorrelation spatially in geographic space. One method that you can use is you can use a package called spthin, and then of course if you're working with MODIS data, then you can apply the minimum distance as the resolution of your raster. So the idea is that each pixel that you're going to have is, or each point that you have is not occurring on the same pixel. So in the case for MODIS data, you'd be thinning it by about 250 meters in the highest resolution, of course. And then so you're going to be organizing your environmental data, typically through principal component analysis that's been used fairly commonly throughout the literature for hypervolumes. And generally, each dimension in the hypervolume, or each principal component that you go with is going to become a dimension in the hypervolume. And so you can estimate how many principal components to use by using a screen plot and kind of eyeballing it. Or you can use a little less subjective method, like the broken stick method, which is then going to be relating the amount of variance explained within your principal components, and then kind of relating that to what would be expected from a theoretical distribution to then get an idea which ones are significant. And then so, yeah, then you're going to be taking your principal components and placing them in a raster stack. Of course, that's not going to be a problem, because if you did your PCA correctly, they're all going to be within the same extent and grain anyway, so that'll be good. And you're going to be extracting data kind of using this framework. I only have this in here calling the specific package just for safety, in case I would either forget to download the library or I have conflicting functions. And then generally after, assuming I'm stacking my my environmental data into an object called environmental layers, I'm just going to be extracting my points into the form of a data frame. And then the idea here is that, say you did not use a PCA for your environmental data, you're then just going to be omitting any records where the data are NA, because that's not going to yield any information for the hypervolume anyway. So in the context of support vector machines, if you're using a default method, you really don't need to write much, except for you need the function hypervolume SVM _SVM, and then you need to take the data that you had extracted from your environmental data and plug that in. The details for the parameter setting of the smoothing within the within your support vector machine and the error rate that you're going to be attributing are all going to affect the tightness of fit. And then, of course, that's going to depend on more details of your study, so that has to be tailored. And I always recommend reading, if you're doing anything in hypervolume, reading that, Blonder et al. 2018 in Methods in Ecology and Evolution is a wonderful starting point because they really dive deep into the functions and parameters that you might want to consider. Yeah, so generally what I would recommend would be assuming you don't have that many points and it doesn't take that long computationally, experiment with different values of gamma. So potentially create a list of values for gamma and nu, and then try to iteratively see the results of different different parameters for smoothing and error rate. That's generally a recommended thing. And then, of course, if you're doing this with KDE approach, the main thing that you need to keep in mind is that one of the major parameters for that, of course, is, as you can infer from when I talked about kernel density estimation, is how you're selecting that bandwidth. And generally, you can use kind of the default Silverman method, which is actually has been shown to yield fairly good statistical benefits. But then you can also use other methods like cross-validation, and that's been recommended to reduce predicted error. Yeah. Other than that, there's a lot of other parameters that that frankly would take a long time to go through here on this short video. The next part is going to be projecting your model into geographic space, assuming that's something you want to do. And you're going to just be using the function hypervolume project. You're calling then your hypervolume object. And then the rasters, it needs a reference raster. So unfortunately, one of the major downfalls with this is you can't transfer the hypervolumes very well, or at all really, into areas that were not calibrated on the model. So it's not that, it doesn't work for transferability quite as well as we might hope. And then, of course, given hypervolume support, or a hypervolume delineated with support vector machines, there's only an in and an out. So then that means that there's going to be areas on the landscape that are considered in and out. So you're only going to be looking at a binary projection. And then verbose equals true just tells you that it's going to be kind of informing you as it's creating the model. You can switch that to false if you don't want your console to blow up, or if you're working on other things. And generally, the only thing you would need to change if you need a continuous map with, if you're doing a KDE projection and you want to understand probabilistically what areas are associated with higher and lower values of probability for suitability, then you would then change the type to then say probability instead of inclusion. And finally, you need to do some form of model evaluation. Again, one of the major downfalls here with Hypervolume is, unlike other programs like Maxent that rely on kind of two sets of data, which will then have a completely independent set for evaluation, and then you actually divide your calibration data into both an inherent testing and or calibration and testing phase to then make sure that you're getting the best available model. Hypervolume doesn't really have that feature. So any form of evaluation that you do on this is going to be evaluated after your model's made. So that kind of emphasizes why you, especially for some of them, if the computational time is very high, you need to be, you might need to experiment around with it first. And generally for the model evaluation side, it's going to depend on the model output. If you're using binary, you can, of course, use a threshold-dependent test, which is then going to be looking at the successes versus trials, and then the proportion of suitable area to then give you a p-value with the cumulative binomial test. And then you can, if you were then using binary rasters also, you can theoretically stack them and then get you an idea which areas are consistently in. And then it's sort of a quasi-continuous model or map then. But of course, you don't really have to worry about that if you're using probability, which is going to be then generating a continuous map already. But then, of course, then you can rely on things like partial ROC and ADC ratios to do your model evaluation. Yeah, so that's all I have today. But I think that, you know, there's a lot more that I could have talked about. But if you have any questions, let me know. Thanks.